Welcome to Design Site-to-Site VPNs. In this video series, we're going to be exploring section 3.2 of the ENSLD blueprint. We're going to be covering all the different ways that we can leverage VPNs to extend WAN connectivity to remote sites. That includes technologies like DMVPN and GetVPN, and just GRE and IPsec, not to mention the Layer 2 and Layer 3 VPNs we talked about briefly in the last video series. So come along with us as we explore all of these different ways that we can leverage VPNs in a WAN environment. And with that, I will see you in the next video. The first VPN technology that Cisco lists would be the Dynamic Multipoint Virtual Private Network, otherwise known as DMVPN. Those are two very key words at the start of that, dynamic and multipoint. Dynamic means a couple of different things. First of all, we can dynamically form tunnels, which is amazing. But we can also form dynamic routing relationships, and we don't have to hard register clients. They can just dynamically come online. And from a multipoint perspective, we can talk from anywhere in the network to anywhere in the network. And so what we're going to find is that this is an extremely flexible protocol that will enable us to talk to not only to remote sites, but also among our remote sites. Let's take a look. DMVPN is going to be one of several overlay protocols that we talk about within this skill. An overlay assumes that we have underlying IP connectivity. So let's say it's the internet in this case. It could also be MPLS, by the way. In some fashion, this Layer 3 interface at one site, let's say our headquarters, needs to be able to talk to the Layer 3 interfaces at our remote sites. Again, let's say this is the internet. These would simply be our public IP addresses that we receive from our service providers. From there, we are going to form tunneled connections among our different sites, specifically from our hub site out to our remote sites, but also even among our remote sites so that we could end up with a full mesh of connectivity. That makes this a point-to-multipoint solution that allows us to communicate with a lot of different sites at once. We can contrast this with a point-to-point VPN. In a point-to-point VPN, we might be able to form a relationship between two sites, and hey, even in this environment, we could make separate point-to-point connections among all of these different locations. But already start to see how many different point-to-point connections we'd have to support in that environment. It would simply be too many. Now, as mentioned in the intro, a key advantage to dynamic multipoint VPN is the dynamic element of it. When we talk about the dynamic nature of VPN, we think of two primary facets. First of all, when a remote site comes online, we don't have to do any configuration on the headquarters in order to bring it into the network. Instead, we put all of the configuration onto the remote site, including the hub location, in our case that would be at the headquarters, as well as our cryptographic key information and passwords and such. And then we will dynamically register with the hub such that all of the routers in our network know where that remote site now lives. Additionally, when traffic arrives on a router in this environment, it's destined for, let's say, a spoke. Maybe down here we'll call it subnet A, living down on the bottom left. At that point, we will build a VPN tunnel that will be torn down once it's no longer needed. Now, the other key element that wasn't mentioned in the intro is the VPN element. We are encrypting this traffic, which means that it's safe to build across public domains like the internet. Now, in order for all of this to work, we need the help of some protocols. Specifically, at the control plane, we are going to leverage a protocol called the Next Hop Resolution Protocol, or NHRP. When a router comes online, as we mentioned, it registers with the hub. And the hub is going to store a mapping of where all of the remote sites in the network live. As such, when this traffic arrives that we mentioned, we need to know where in the network that's destined towards. At that point, we'll send a resolution request up to the headquarters, which will respond with the public IP address of the remote site. Now we know how to build that tunnel down to the remote site. So again, NHRP at the control plane is a mission-critical component of DMVPN. Meanwhile, at the data plane, we are leveraging multipoint GRE, otherwise known as MGRE. MGRE allows us to build a single tunnel interface on a router and create multiple tunnels from that one interface. So we look up here at our hub, and the fact that it's got connections to all of these different routers, we still only have a single tunnel interface. Yet we're able to build multiple tunnels out of that to all of these different sites. That's thanks to multipoint GRE. Furthermore, we are going to leverage IPsec for encryption. And lastly, because we're leveraging GRE, we are able to carry routing protocol information across the data plane. Not all VPNs allow for this, so the fact that we can form an EIGRP relationship, let's say, between these two routers, that's a big deal because now we can completely control the routing relationships in our environment. So how can we leverage DMVPN within our designs? Well, first of all, as mentioned, this allows us to leverage the internet. And when we're deploying traffic across the internet, usually what that means is we're going to use that as a backup WAN circuit. So for example, we might have our headquarters connected to the remote site via an MPLS provider, but then also we've got an internet circuit here. We've got an internet circuit at both sites, in fact. So we could leverage DMVPN as the backup connection. Now, if we do something like this, we remember that we are redistributing routing protocols into MPLS, whereas we can form a direct routing relationship across DMVPN. In a lot of cases, this will mean that this will become the preferred route by default, and that's not usually what we want. If it's going to be the backup WAN circuit, we're going to have to tune our routing protocols in order to make that happen. Now these days, in some cases, the internet is good enough quality that we can consider it as our primary circuit. However, that does carry with it some amount of risk, because if the quality of service of the internet circuit tanks, then we're going to need to switch over to a reliable connection. So maybe MPLS in this case is our backup circuit. However, something to consider with our designs is that failing over between links isn't a super straightforward process. It's going to take a lot of configuration in order to make that happen, and that's an area where SD-WAN can really help us out, and we'll be covering more about SD-WAN later on in this course. Now all that said, we could also deploy DMVPN over an MPLS connection. I will say that in my experience, most DMVPN deployments are going across the internet. However, there is a lot of value in building it over MPLS. So let's update our drawing here and make this an MPLS provider. And again, think back to how we interface with MPLS providers. We have to exchange routes with the MPLS provider and trust that they're going to send it across their environment. Furthermore, they are not encrypting our traffic for us, and this is a shared environment. So they have all of their different tenants sharing their infrastructure, and our packets are being switched right along with all of the other organizations in their network. Well, if we build DMVPN tunnels across the MPLS provider, this solves a couple of different problems for us. First of all, we can build direct adjacencies across the DMVPN tunnels. So we no longer need to exchange routes anymore with the service provider. Instead, we can form direct EIGRP or OSPF relationships with our other routers. Second of all, this provides traffic encryption, which means that now our traffic is protected. Yes, on some level, we always have to trust the service provider to do their job, but it sure would be nice to have our traffic encrypted just in case they make a mistake. Now, while this looks great on paper, unfortunately, this can come with a pretty big caveat, which is that we need to consider MTU as part of this. Any tunneling mechanism is going to require us to increase the MTU of our underlay network. And unfortunately, when the underlay network is MPLS, that network is outside of our control. At that point, we have three primary options, none of which are necessarily going to work out great for us. The first of which is to simply fragment our packets. That's going to put a lot of CPU strain on our routers and also add some latency into the network. The second option is to lower the MTU at our clients. Unfortunately, this is really tough to do because we're talking about going out to all of the different clients in our network and tuning their MTU to be lower than the default setting of 1500 bytes. Fortunately, we do have the option of something called path MTU discovery, which we'll talk about in a little bit more detail in the coming video. Lastly, we can always ask the service provider simply to support larger MTU sizes, but unfortunately, this just isn't always an option. Now, certainly if it is an option, that would be our preferred choice. Unfortunately, if it's not, then we're going to have to go with one of the other two options in order to make this all work for us. Now, a couple other design factors that we'll want to consider. First of all is redundancy. We mentioned NHRP earlier, and NHRP is going to store its database on the hub. As such, we should always deploy a second hub into the DMVPN environment. Now, the second hub can exist at the same site, so by all means, deploy it to the headquarters location. Or if that's not an option and we don't want to purchase additional hardware, we can turn one of the other remote sites into the backup hub. So yes, let's make sure that we have two hubs, but another consideration could be that we would want to deploy two different DMVPN, well, let's call them clouds. Essentially, each instance of DMVPN would be its own cloud, and as such, if we were to deploy two instances of DMVPN, well, that would add additional redundancy. Another factor we have to consider is how dynamic we want this environment to be. We can block spoke-to-spoke traffic if we desire. While it's certainly more efficient to have spokes be able to talk directly with one another, the way our traffic patterns work these days is that we're often going to headquarters resources, whether that's a data center or even a centralized internet circuit. You say, well, Jeff, we're building DMVPN on the internet, let's just use our local internet circuits. Except in a lot of cases, we've got centralized policy management at our headquarters location, and so we might still want to send all of our traffic up to the headquarters. At that point, there's not a lot of spoke-to-spoke traffic happening anyways. So by disabling spoke-to-spoke traffic, yeah, it's less efficient, but in a lot of ways it allows us to enforce our policy a lot better. We also need to consider NAT. If for any reason this router is behind NAT, such that it is being padded out to the internet, well, that's going to create problems for us. We cannot provide connectivity between two different routers that are using port address translation. At that point, the tunnel would not form. So it's just something to consider. In a lot of cases, we're not going to have to worry about this. But at the same time, absolutely, if our remote sites are behind a PAT, then we probably cannot enable spoke-to-spoke communications. Lastly is licensing. When we're licensing our devices, we might need to consider an additional security license depending on the number of tunnels. And for that matter, we might need to consider additional hardware. All of this should be tied to the number of tunnels that we're going to be forming in our environment. Larger hardware will mean more tunnels, but in some cases, we are restricted to the number of tunnels that we can use without, again, adding an additional security license. The last thing we want to do is buy a bunch of hardware from Cisco, send it out to our remote sites, and find out after the fact that it cannot support the environment that we've designed. So, when we consider DMVPN for our WAN circuits, we need to think about a few things. First of all, DMVPN is, as the name implies, it's dynamic, it's multi-point. Its sites come online automatically, and we form GRE tunnels as needed. And speaking of which, at the control plane, we're using Next Hop Resolution Protocol, NHRP, and at the data plane, we're using MGRE, multi-point GRE, in order to form all of those connections. Furthermore, we're using IPsec for encryption at the data plane. Now next, we can build DMVPN over the internet, over the public internet, for example. We can also build it over MPLS, or really any network can serve as what we call the underlay. As long as we have connectivity among all of our routers to build the VPN tunnels, that overlay network, then we're good to go. Lastly, when we're doing our designs, we want to consider a whole lot of things. We've walked through a lot of options in this video, but especially think about redundancy and think about all the different configuration choices that we have available to us. I hope this has been informative for you and I'd like to thank you for viewing. Layer 2 and Layer 3 VPN services are some of the most popular WAN connectivity types out in the market today. In this video, we're going to explore all the design principles we need to consider when looking at these options. Let's take a look. If you're working your way through the ENSLD course, then we just covered Layer 2 and Layer 3 VPNs in the last skill. But as a quick review, when we're talking about this concept of Layer 2 and Layer 3 VPNs, really what we're talking about is a provided service that's going to connect our remote sites via a shared infrastructure with other customers. Which means really what we're talking about is the service provider builds a VPN for us and ensures that we are going to have private communications among our different sites. One thing to keep in mind in all of this is that this traffic is not encrypted. Usually when we're talking about VPN services, we're assuming there's some level of encryption, but keep in mind that that is not a strict requirement of VPN. All our service provider is ensuring is that other customers, let's say we have a customer out here that doesn't belong to us, we're customer A, they're customer B, they're ensuring that our traffic will never see each other. Instead, traffic that's destined for another customer B location, that can pass through without interfering with our traffic, and likewise our traffic will pass through the service provider's infrastructure without crossing paths. Now there are two primary ways of building VPNs, and it's right there in the title of this video, Layer 2 and Layer 3. From a Layer 2 perspective, we're usually talking about VPLS or VPWS. VPLS stands for Virtual Private LAN Service, and that is a point-to-multipoint solution. Meanwhile, VPWS is Virtual Private Wire Service, and that would be point-to-point. These services will extend Layer 2 among all of our locations, so all of our routers in our example could have a Layer 3 interface that's part of the same subnet. Let's say 10.0.0.0/24, with .1 showing up over here, .2 here, .3 here, etc. But then we have Layer 3 VPN services, and that's almost always going to come down to multi-protocol label switching, or MPLS. When we have a Layer 3 VPN design, we are going to have Layer 3 connections to the service provider themselves. So maybe this is a /30 on this link, this over here could be a /30, it could be a /29, but either way we have Layer 3 segmentation among all of our routers. Now in order for us to exchange routes between these two locations, let's say this is Site 1 and Site 2, well I'm going to have to share my routes with the service provider, and they're going to have to share those routes with Site 2 on my behalf. That means I'm running a routing protocol with my service provider. That means maybe BGP, for example. But the point is I do not have Layer 2 access with all of my sites. I have Layer 3 access, and at that point I have to exchange routes with my service provider directly. So that is a quick review of what Layer 2 and Layer 3 VPNs look like. If you want more details, then be sure to go back and check out the skill called Compare WAN Connectivity Options that's part of this ENSLD course. Now when we're considering VPN services relative to other WAN connectivity options, we're going to want to consider a few things. First of all, VPNs tend to be very high bandwidth. We're not talking T1s and E1s, we're talking about 10 meg and 50 meg and hundreds of meg of throughput that we can get on MPLS and VPLS and such. We also see low latency. This is huge for voice over IP. If I have telephony, for example, at my two different sites, I'm going to communicate between my phones. Well, I need this infrastructure in here to be extremely low latency, extremely low jitter. And these VPN services are fantastic for that. They also tend to be highly reliable. Service providers like to tout their uptime. We can see 4 nines or 5 nines of uptime in a lot of cases. And so far, this is all looking really, really good. But of course, there has to be a downside to VPNs, and the typical downside tends to be the cost. VPN services are usually a whole lot more expensive, especially compared to internet circuits if we want to run our own VPNs across the public internet. But you get what you pay for in a lot of cases, and the philosophy over time has always been that if we need high bandwidth and we need low latency and we need high reliability, then yeah, we're just going to have to pay the money in order to make that happen. If we do decide that we want to move forward with a VPN service, then we have to decide between layer 2 and layer 3. Layer 2 has a couple of key advantages. First of all is no route sharing. If your data governance policy is going to have a problem with sharing routes with the service provider, then you're not going to like MPLS a whole lot. Now, I can tell you that from an industry perspective, the industry considers this to be relatively safe practice, and so it's not uncommon for banks to even participate in this route sharing methodology. However, you have to make your own decision based on your organization's needs. And so if route sharing is a problem, then layer 2 is absolutely a way that we want to go. Because at that point, we are going to be able to share routes directly among our remote sites. Second of all, one of the values of layer 2 networks in general is the flexibility that it affords. When all of these sites are on the same subnet, then we can do whatever we want with them. We can run a lot of different protocols that we can't run in a layer 3 infrastructure. Now, conversely, layer 3 also has some benefits. First of all, it does tend to be a little bit more available than layer 2 services. In other words, I might go to my service provider all prepared to say, hey, I want to order layer 2 services to all of my remote sites. And they might come back and say, oh, I'm sorry, we can't actually deliver VPLS out to this remote site that you want to extend it to. So at that point, we're stuck with layer 3. Second of all, scaling is better with layer 3. This is always the case, whether in campus infrastructures or with wide area networks. But if I have hundreds of sites on this WAN cloud and I'm going to build this on layer 2, well, all of a sudden I'm going to have a whole lot of EIGRP and OSPF neighbors on this one broadcast domain. Because yes, if it's layer 2, we're talking about broadcasts. Now, if we're going to scale up on a layer 2 domain, then we probably want to consider OSPF, because OSPF can handle broadcast domains a little bit better than EIGRP. EIGRP, if we have 50 routers, all 50 routers are going to have relationships with the other 49 routers. Whereas with OSPF, we have this concept of designated routers, and that's going to greatly assist us in scaling this out to all of the different routers. Now, another advantage to layer 3 is that we can get additional services delivered to us. For example, my service provider can actually deliver internet via the MPLS circuit. We could have an internet cloud hanging off of the MPLS circuit, and therefore my remote sites go into the MPLS cloud and access internet that way. In those cases, we probably have a cloud firewall service in there as well. Another service we could consider would be management of our remote gateways. Let's say we have a site with just a few users and we already have a switch out there, but we don't have layer 3 services. Well, rather than installing a router like we do at some of our other sites, we could simply connect up to the provider edge router. And the provider edge router, because it's part of the routing domain, can provide gateway services. So whether we have a single VLAN or maybe a small handful of VLANs, either way, the service provider manages this for us, and we no longer have to deploy layer 3 hardware out there that we have to configure and manage. These services are available because the service provider is part of our layer 3 infrastructure at this point. So while that can be a disadvantage to some organizations, viewing that as a violation of our data governance policies, security policies, etc., it can also come with some advantages, as we see here. Now, one more thing we'd want to consider in all of this would be redundancy. And when we talk about redundancy, we might be talking about redundant circuits, we could be talking about redundant routers, and even redundant providers. Now, we're going to be covering redundancy in more detail later on in the ENSLD course, but just something to keep in mind that as part of any WAN design really, including layer 2 and layer 3 VPNs, we absolutely want to consider redundancy as part of it. So once again, when we're dealing with WAN circuits, VPN services are going to be some of the most common WAN connection types that we see. Whether it's layer 2 VPLS, for example, or layer 3 with MPLS, either way, we're probably going to see a lot of this in our environments. And second of all, VPN services are very high quality, but they do come at a cost. So if we need that bandwidth, for example, if we need latency reduction, if we need improvement of reliability, then we're probably going to want to consider VPN services. At that point, it's usually worth the cost. But just keep in mind, it is more expensive in most cases than other solutions, especially internet-based services. Third, layer 2 and layer 3 VPNs, they each have their upsides and downsides. We talked about a lot of those. A lot of it comes down to how comfortable we are as an organization with sharing information with our service provider. So keep that in mind. And lastly, as part of any WAN design really, but certainly as part of VPN design as well, always consider redundancy, whether it's multiple circuits, different hardware, different service providers. Either way, we want to make sure that we always have available to our remote branches. I hope this has been informative for you, and I'd like to thank you for viewing. In learning about DMVPN, we just discovered that we are using GRE tunnels between the routers at our different WAN sites. GRE, or Generic Routing Encapsulation, is a tunneling mechanism that Cisco devised many years ago in order to transport non-IP traffic through an IP infrastructure. Think about things like IPX and even AppleTalk, I suppose. Now these days it's all IP, and yet we still rely on tunnels for a lot of architectures. DMVPN is one example. Software-defined networking, or SDN in general, relies heavily on the use of tunneling mechanisms. So in this video, we're going to explore what exactly it means to tunnel traffic, as well as how GRE does it specifically. So let's take a look. When we first started learning about networking, we talked about this OSI model and the concept of encapsulation. Encapsulation taught us that we can take our data, encapsulate it inside of a layer 4 header, such as TCP, let's say, and then that we encapsulate inside an IP header, and from there we encapsulate it inside of Ethernet. And we're encapsulating, and really what we're doing is we're hiding information further inside the packet that will one day be processed. For example, when this frame arrives on a layer 3 switch, it's going to strip off the Ethernet header and look at the IP information. And if the IP address happens to be destined for itself, hey, it can strip off that and look at the TCP information inside. And the point is that we don't look further inside the packet at the information that's stored until it's relevant. Well, as mentioned, GRE was developed to hide information inside. For example, packet information that can't typically be read by an IP packet. For example, back in the day, we might have had a fully formed IPX packet that now needs to traverse an IP network in order to get to the IPX host on the other side. And the way we accomplish this is by treating the entire IPX packet as the data payload. From there, we can do what we typically do. We encapsulate that inside of a layer 4 header, and we encapsulate that inside of a layer 3 header, and we encapsulate that inside of an Ethernet header and push it out onto the Ethernet network. As the packet traverses the IP network, it's going to be hitting routers and switches that are IP driven. Layer 2 switches, for example, are going to look at the Ethernet header to try to figure out where this MAC address lives. And then when we get to a router or a layer 3 switch, it's going to look at the IP information to figure out where in its routing table it should send it. Ultimately, once we get to the other side, it's going to strip off all of the TCP IP information and forward on the original payload. And that original payload is an IPX packet that can now be received by IPX switches and forwarded onto the network as needed. Now these days, we're not doing a whole lot of IPX transfer, but we are still relying on these tunnel mechanisms. And we talked about why, for example, with DMVPN, we're able to form tunneled connections between the routers at our different locations. When we're talking about tunnels, we're talking about hiding information from the underlay network. So for example, I might send traffic onto a service provider router, and the service provider router has no idea what I'm doing inside. It's only going to see that, okay, I'm trying to get to this router, and it will forward the traffic to that router, and that router will de-encapsulate it and send on the original packet. The way we do this today is we're going to take a fully formed IP packet and we're going to encapsulate that inside of a GRE packet. We're going to put a special GRE header that contains information in here that will help us tunnel the traffic. This header is only 4 bytes in size, but it can actually increase as we add additional options. So we have to be careful about that in our MTU calculations. Next, we put another IP header in front of it. And it's this IP header that our underlay routers are going to look at as we're forwarding the packet. So again, our service provider router over here in the DMVPN domain, it's looking at the source and the destination IP address that's in the outer header. The original IP header that contains the original source and original destination address, those are hidden. They are not processed by the routers that are forwarding this traffic. So if the packet arrives and its destination address is, let's say, some kind of 192.168.something.something, well, now our service provider routers don't have to know where 192.168 is. Instead, maybe we're using a public IP address of 1.2.3.4, and our service provider just needs to know how to get to this public IP address, which, hey, it's an internet service provider. It should be able to get us there. Now, alas, anytime we talk about tunneling mechanisms, we have to bring up that dirty word of MTU, maximum transmission unit. Because if I take a 1500 byte packet and I add to it another 20 byte IP header and a 4 byte GRE header, well, this packet grows in size to 1524 bytes. The problem is a lot of my routers are configured to send to the service provider at 1500 bytes. Now, the good and bad of IP is that it can support fragmentation, which means we can be sending packets to the service provider that are far too large and never realize it, because our router is going to fragment that oversized packet and send it upstream as 2 smaller packets. Now, this could be the end of the conversation because we could simply allow our routers to fragment and then defragment that packet on the other side. Unfortunately, this comes with a pretty big downside of CPU utilization. Especially if we're encrypting this traffic, which we'll be covering in the next video, it's going to really hit the CPU pretty hard if we rely on this as our primary mechanism. Now, we talked about this in the DMVPN video as having a few different options, and those options, just to quickly review, are to either increase the MTU if we can. That would be great if we could simply set the MTU to 1524 bytes or maybe something better like 2000 bytes just to give us additional overhead on the underlay network. If we're in charge of the underlay network, then this is certainly an option. But in a lot of cases with wide area networks, we're not in charge of the underlay network, and so increasing the MTU size on the underlay is not an option. Now, another option we mentioned is lowering the MTU on our hosts. The NPCs and devices and phones and such that are sending their packets, they have the ability to do something we call a path MTU discovery. The path MTU discovery is going to take a packet and send it across the network to try to figure out what that MTU really is. And if on our routers we set the TCP maximum segment size, or TCP-MSS, if we set that appropriately to the right value, then the path MTU discovery will help the end clients do what they're supposed to do and send smaller packets. If we don't have control over the underlying MTU, then this is certainly our next best option, but we're going to have to make sure that our end devices are properly doing their path MTU discovery. Now lastly, we can always still rely on fragmentation, but as mentioned, it's not ideal from a CPU perspective. Our router CPUs can take a dive if we're sending large enough packets at a fast enough rate. Now in most cases, we're going to pair GRE up with IPsec in order to do packet encryption, and that's exactly what we're going to cover in the next video. So as we think about GRE, we think about the fact that encapsulation can be used to hide information within the packet itself. And so we can put an additional header on front, and essentially, again, this is the word tunneling, right? We're tunneling that traffic through an underlay that either can't understand what's inside the packet, or just we don't want them seeing it. Now, when we're using GRE, it's going to add a minimum of 24 bytes to the header. So keep in mind that there are options that could expand that further. And as we're going to see in the next video, if we decide to encrypt this traffic with IPsec, it's going to increase the header size even further. So our MTU considerations are just continuing to rise. As such, when we think about MTU, we have three main options available to us. We can rely on fragmentation, and honestly, there's a lot of networks out there that are accidentally relying on fragmentation, not even realizing it. But we don't usually want to do that. If that's our decision, fine, but let's be intentional about it. Otherwise, we can increase the underlay MTU. That's certainly an option. Otherwise, we can decrease the client MTU, which, yeah, can be a manual change, and that's not ideal. But if we can make sure that path MTU discovery is working, then our clients will do that for us, making our lives a whole lot easier. I hope this has been informative for you, and I'd like to thank you for viewing. DMVPN is going to take advantage of GRE in order to form those tunnels to the remote sites. But the other component of DMVPN is that it also encrypts the traffic. Well, GRE doesn't help us encrypt it, but IPsec will. In this video, we're going to explore how exactly IPsec encrypts traffic in a data payload like GRE, but then also the design decisions that we have to make around IPsec. Let's dive in. The first thing to know about IPsec is that it is not a protocol. We in the industry sometimes refer to it as a protocol. It's a bit of a misnomer, because really IPsec is a framework that's going to leverage protocols in order to get us where we want. So the question is, what are we trying to accomplish here? Well, in the security world, there are three different facets that we need to consider. First of all is authentication. Authentication means, do I know for sure that you are who you say you are? Second is data integrity. Data integrity asks the question, is the packet I just received exactly what you sent to me? Did somebody in the middle grab the packet and change the data inside before sending it on to me? And lastly is confidentiality. When most of us think of IPsec, we probably think of confidentiality, because confidentiality is really data encryption. It ensures that nobody else has seen the contents of the packet other than the sender and the receiver. Now, since IPsec is a framework and not a protocol, it's going to give us several options for how to accomplish what we're trying to accomplish from a security perspective. And the first protocol we can use is called Authentication Header. Authentication Header, otherwise known as AH, is a protocol that enables, first of all, authentication, go figure, based on the name, but also data integrity. However, Authentication Header is not going to do anything for us from a confidentiality perspective. In other words, it does not encrypt the traffic. Now, since for most of us, our primary goal is confidentiality of the data that we're transmitting, Authentication Header is probably not going to be used in most cases. Instead, we're probably going to use the other protocol that's available to us, which is Encapsulating Security Payload. Encapsulating Security Payload, or ESP, is going to do all of these. Yes, it does authentication for us. Yes, it does data integrity for us. And yes, especially the one we care most about in this conversation, it's going to give us data confidentiality by encrypting the traffic. Now, there are two ways of accomplishing the data confidentiality, and it gives us two options for our network designs. We have transport mode as an option, and we have tunnel mode. The difference between these is going to come down to whether we want to encrypt the IP header. Tunnel mode is going to encrypt it, whereas transport mode is not. In order to understand how this works, we need to break down the packets one more time. As we recall, we have an original payload that was sent to us by a client, and we took that and we added a GRE header and an IP header. However, now we have new headers, whether it's authentication header or ESP, either way, we're going to have to insert that header into this packet. Now this IP header is the outer IP header from a GRE perspective, and that needs to stay on the outside so layer 3 devices can read it. As such, we're going to strip that IP header off and add the ESP or AH header, which incidentally is another 16 bytes. At that point, we put the IP header back in front and we send that packet on its way. Now, what we need to understand from this packet diagram is that ESP is responsible for the encryption, as we've said, but since it's responsible for the encryption, it's only encrypting everything in here. It is not able to encrypt what's in front of it. Which makes sense, by the way. We need that IP header to stay unencrypted so that layer 3 devices can read it and know how to forward it on to its final destination. But the thing is, there's other information inside this IP header besides source and destination address. And if we decide that's worth encrypting, then we probably want to look at tunnel mode. Tunnel mode is going to take that original packet that has a GRE header in front of it, but it's going to leave that GRE outer IP header in place. Keeping in mind, by the way, that we have an inner IP header in here as well. Then we put the ESP header in front of that, and now it's able to encrypt the entire packet, including the original and outer IP headers. Now we've added 16 bytes for ESP, but also another 20 for that original IP header. Now we're not done yet, because when routers receive the packets, we've got to be able to see a source and destination IP address, and so we do still build yet another IP header. This is the third IP header in this packet, and we're going to copy key information into the IP header from the IP header that we just encapsulated. But we're not going to copy all of the information. This way, as the packet traverses the network, the unencrypted IP header can be read by anybody in between, but there's no real information in there that they can use to figure out what's going on inside the packet. So whenever we're designing an IPsec environment, we have to make two different design decisions. First of all, we have to decide between AH and ESP, and second of all, we have to decide between transport and tunnel modes. Now this appears pretty straightforward, right? We're going to use ESP and tunnel mode because they are the more secure options. However, pay attention to what's happening with ESP and tunnel mode. We're adding additional overhead. We are adding not only the encryption process, which is going to require additional resources on the routers, but we're also increasing the MTU pretty significantly, especially with tunnel mode. So we have to balance these. However, I will say that yes, in most real world scenarios, we're going to use ESP, we're going to use tunnel mode. That is usually how it's going to be deployed, but we need to understand the implications of that just in case there's anything in our environment that's going to cause problems if we deploy ESP and tunnel mode. So when we're looking at IPsec, let's keep in mind that it is a framework, not a protocol. It gives us several protocols we can use to try to accomplish what we're trying to accomplish, which is usually data integrity, data confidentiality, and data authentication. Now, when we look at authentication header, it is great, as you can imagine, at authentication. It can also do data integrity, but it is missing encryption. It can't do data confidentiality. If we want that, then we're going to have to look at encapsulating security payload, or ESP. ESP does all three. It gives us data confidentiality, the encryption that we need, in addition to authentication and integrity. Now lastly, we have to decide, when we're deploying ESP, between tunnel mode and transport mode. Tunnel mode is going to give us encryption of the IP information by giving us a third IP header inside of this packet. But at the same time, if we don't need that, then we could look at transport mode, and transport mode isn't going to encrypt the IP header. We have to decide sometimes between the resources that it's going to consume and the effort we're going to have to go through not to fragment packets versus whether we really need that information encrypted. That's part of us as a design engineer having to find the right fit for our environment. I hope this has been informative for you, and I'd like to thank you for viewing. Sometimes when we solve a problem, the solution itself can have some problems. For example, we look at DMVPN. DMVPN is fantastic because it's dynamic and it's multi-point. But as we scale that up, we realize that that multi-point is a little bit of a misnomer. Because what's really happening under the hood is we're forming a lot of point-to-point GRE tunnels, and we're tunneling point-to-point among all of our routers. Well, yeah, I mean, effectively that is multi-point, but when we scale that out to dozens of routers in our environment, sometimes our network starts to slow down from the teardown and creation of all of these different tunnel interfaces, and things like multicast don't work so great in a unicast environment. So enter GetVPN. GetVPN is a solution that might solve some of the problems of our previous solution. Let's take a look. When we talk about DMVPN, we have this hub and spoke methodology, and the idea here is that we can dynamically form tunnels among any of these locations at any time. However, even though we're leveraging multi-point GRE or MGRE, we're still going to form individual tunnels among all of these sites. So now let's say we have a phone call that's going to happen between these two sites here on the right, and so the voice call starts, and this router knows now that it needs to form a new tunnel to that site. Well, setting up this tunnel is a process. We have to exchange keys and build the tunnel, and that's going to take time such that this traffic is just going to be dropped until that tunnel is established. Furthermore, if multicast traffic were to show up at one of these sites, we're going to have to dynamically form our tunnels to every other location that needs to receive that multicast traffic, and at that point, we're sending the multicast traffic via these unicast tunnels. Ideally, we would only send one packet into the infrastructure and it would replicate to all of the sites on an as-needed basis. But unfortunately, we can't take advantage of that efficiency by leveraging multicast in this case. Now, as we can see, with 4 routers, none of this is that big of a deal, but imagine dozens of routers or potentially even hundreds of routers in this environment. When that's the case, this point-to-point tunneling mechanism isn't going to be particularly ideal. This is where GET VPN comes into play. GET stands for Group Encrypted Transport, and it was developed by Cisco. And the most fascinating part about GET VPN is that it is tunnelless, which effectively means that we are not using GRE. It also abandons the hub and spoke topology of DMVPN in favor of any-to-any communications. Both topologies are point-to-multipoint, but any-to-any has no concept of a hub. So that's great, but what does this functionally mean? First, let's look at tunnelless. If we are bringing a packet in and we're going to encapsulate into that point-to-point GRE tunnel, then we have all of the problems that we talked about before. But if we're not encapsulating into a tunnel, then we can simply send it to our destination natively into the infrastructure. If we're natively sending it, then first of all, we don't have to worry about multicast anymore, because multicast will be natively handled by the underlying infrastructure. Second of all, we can natively look at IP flags like QoS. Finally, because it's tunnelless and because it's an any-to-any topology, we don't need to form tunnels anymore. We can simply bring a packet in and send it to the appropriate destination wherever that might be. So that allows for very fast forwarding of this traffic. Now in the US, we have an expression: if it sounds too good to be true, it probably is. And indeed, there is a downside to GET VPN, and that is the fact that it does not support public infrastructures. That's one of the reasons why we use GRE, is to tunnel through the internet. And so GET VPN is meant for private infrastructure. So maybe we have private LAN and WAN extensions, but in a lot of cases, this is going to boil down to using MPLS or VPLS or some other private VPN service from a service provider. Now here's the reason for this. We are still leveraging IPsec, and we're still leveraging ESP. In fact, we are leveraging tunnel mode, even though we're not actually tunneling packets. But that's just it. If we're leveraging tunneling mode, then what are we using for the source and destination IP address, since we no longer have a tunnel to use? This is where we have this concept of IP preservation. When we form our packet in GET VPN, we're going to have the original payload with the embedded IP header, but we're not using GRE, so right away we put down the ESP header, and then we build this outer IP header. Well, when we build this, this is simply going to be a copy of the internal IP header. And that includes the original source and destination addresses, which might well be RFC 1918. In other words, it might be private addressing. So we could have a destination address in the outer header of 192.168.1.1, and we can't send that out onto the public internet because it's a private address. As such, when we zoom out, we see that GET VPN is designed to give us a whole lot of neat advantages, but only if we're not going across the internet. Now, when we look at the GET VPN architecture, we still have some questions to answer. For example, in DMVPN, we had the concept of a hub, and it was running NHRP, and it stored the database of all of the remote routers. But we don't have that concept in GET VPN. So where are we storing the control plane information, and what protocols are we running? Well, the control plane information is going to be stored on what we call the key server. The key server, or the KS, is going to be a router that we simply configure to act as the key server. Now remember, one of our goals with GET VPN is to solve the scaling issue. And so what we're going to do is we're going to put all of the policy information onto the KS. We're also going to put all of the key management onto the KS. And so this information no longer needs to be stored on the other routers, which we're going to call group members. Now we're not going to run NHRP in this environment. Instead, we're going to run a protocol called Group Domain of Interpretation, or GDOI. So even though from a data plane perspective, we're not running hub and spoke, we do still have a node that is responsible for control plane information. As such, it's usually recommended that we deploy 2 of these for redundancy into the environment. Now, we mentioned before that the other routers in our environment are called group members, or GMs. Group members are going to reach out to the key server in order to get all the information that they need. This is primarily going to revolve around the security association and the keys that it's storing on the key server. The interesting thing is that we are sharing a security association. And what that functionally means is that if we're going to send a packet out into the infrastructure that's been encrypted, then any one of the other group members can receive that packet and de-encrypt it. Thinking back to DMVPN, where we had individual tunnels among 2 different sets of routers, let's say, well, if I were to send traffic out this tunnel, it would be able to be de-encrypted by the other side, but it could never be de-encrypted by a different router because it's a different security association. Once again, the downside to this is the fact that we have to build and establish all of these point-to-point tunnels. Instead, because GetVPN is focused on scaling, and we have this concept of a shared SA, we're able to take any packet that comes in and simply send it out towards its destination, and we don't have to pause everything to build tunnels. We don't have to pause everything to encrypt it a different way. We simply send it into the domain encrypted the same way regardless of the destination. This greatly speeds up our spoke-to-spoke communication as well as communication anywhere within the domain. So when we look at GetVPN, and the goal we're trying to accomplish here is to build a faster, more dynamic DMVPN essentially. And so the way we accomplish that with GetVPN is by making a tunnelless architecture. And we leverage an any-to-any topology instead of using hub and spoke. Now the downside to GetVPN is that it is only for private transport. We are thinking of things like MPLS or maybe even our own private connections rather than sending it out across the internet. One of the reasons we can't do that is because of that IP address preservation concept. Now, the way we accomplish all of this is by deploying a key server and group members. So with the key server, its focus is going to be storing all of the keys and security associations. And again, we want to consider deploying these redundantly for the fact that we don't want to lose one. It would take our GetVPN environment down. And the group members are going to go to the key server using that as the control plane mechanism. In other words, we're going to use that GDOI protocol. And from there, we're going to get the security association that's shared among all of our routers. And now we can just natively encrypt and forward that traffic into the infrastructure, which gives us all of the advantages that we discussed. I hope this has been informative for you, and I'd like to thank you for viewing. We are making some great progress in this ENSLD course, and in fact, we've come to the end of another skill. So let's review what we've learned by taking this quiz. First up, out of 5 questions, identify the control and data plane protocols used in DMVPN. Well, on the control plane side, we are going to leverage the Next Hop Resolution Protocol, or NHRP. On the data plane side, we need to encapsulate that into tunnels, and we are going to use multi-point GRE, or MGRE, as our protocol of choice. As such, NHRP and MGRE, these are the 2 protocols that come together to make DMVPN happen. Next up, what are the advantages of Layer 2 and Layer 3 VPN services? Well, when we think about these VPN services, we're thinking of things like VPLS for Layer 2 and MPLS for Layer 3 VPN services. And when we think about these protocols, usually what that's going to come with are high bandwidth and high reliability connections. But unfortunately, that does come at the cost of, well, cost. It's going to be a little bit more expensive to rely on these services, especially compared to traditional leased line services. Now, even though it's called VPN services, we do not encrypt anything. We are simply making it private from other customers that are leveraging the same network. So customer A going into the MPLS domain isn't going to be mixed with customer B traffic that's sharing the infrastructure. That's what we mean when we talk about this being a VPN service. As such, we don't get native encryption. We don't get a low cost of operation. In the end, what we get are high bandwidth and high reliability. So B and C are our answers. Question 3. What is the minimum header size for GRE? And the key word here is header size. We talked about the fact that the GRE header has a minimum of 4 bytes in it. Yes, if we include the IP header, because we do need a second IP header, then that adds another 20 bytes, and so our eyes might have fallen to 24 bytes, but that really is the 20 bytes for IP plus the 4 bytes for GRE. Now, when we're taking the ENSLD, if they were to ask us something like this, we need to pay special attention to exactly the wording of the question. Because if they ask for the header size for GRE, well, that's 4 bytes. But if they ask for the minimum MTU increase for GRE, well, that would be our 24. Next question. Which IP set configuration will encrypt the packet payload without protecting the information in the IP header? Well, first of all, encrypting the packet immediately takes authentication header out. Authentication header is great at authentication and data integrity, but it doesn't do data confidentiality, which is encryption. So A and B are immediately out. Next, we need to pay attention to the fact that we're protecting the payload, but we're not protecting the information in the IP header. We recall that tunnel mode protects both the payload and the IP header, whereas transport mode is only going to protect the payload. As such, C is our answer here. ESP gives us the encryption that we need, and transport mode ensures that our payload is encrypted, but doesn't do anything for us in the IP header. Last question. When leveraging GetVPN, which component of traditional VPNs is no longer required? When we're using GetVPN, we are absolutely going to encrypt that traffic. We are absolutely going to use IKE, the Internet Key Exchange, In order to negotiate that, that wasn't part of our conversation, but it is in the back-end processes of how encryption is established. Now, we did talk about the fact that we use key servers in GetVPN. It's an important component of a GetVPN architecture. However, we do recall that GetVPN is this tunnelless architecture concept. We are no longer establishing tunnels among our endpoints. Instead, we receive a packet, we encrypt the packet on our router, and we send it out towards its destination. We don't have to worry about where the destination is before we encrypt the packet. Nor do we have to encapsulate that packet into a tunnel and send it out at that point. As such, D is our answer. Well, that wraps up this quiz. If you find yourself missing any of these key pieces of information, then make sure to go back and watch the appropriate video in order to absorb all of that data. Otherwise, congratulations on completing Design Site-to-Site VPNs. I hope this has been informative for you. I'd like to thank you for viewing.